21. All right, guys, so today's notes are on vector fields, and I am on slide 21 if you want to follow along with me. A field, when we talk about fields, and we've talked about field forces already, and of course right now we're going to talk about vector fields, but a field is a region surrounding an object in which a second object will experience a force at a distance. So Earth's gravitational field extends obviously past the surface and into the space around the Earth, or at least in close proximity relatively to the Earth's surface. And in that space, objects will experience that force of attraction and they'll fall towards the surface of the Earth if they're close enough to it. Okay, and thus, because the field has direction to it, it is called a vector field, because again, things are going to fall toward the surface of the Earth. So how do we visualize a field? Because obviously we can't see it in the real world, but we can model it, and we can model the field based on how it influences objects that interact with it. Okay, so we can look at how it affects other things, and the model is called a vector field diagram. Okay, so we're going to start our discussion of vector fields by talking about our vector field diagrams. These are models used to represent the forces exerted by a field at various locations in the field. We use vectors at points around the source of the field, but we can't show every point. Okay, you can't show an infinite number of points and an infinite number of vectors, because obviously that would be a giant mess and you wouldn't be able to see it, and things would overlap and all of that. Okay, and so we just choose kind of regularly spaced points, if you will. You'll see it in a second. And the length of the vector that we draw at each of those points will indicate the strength of the field at that location. The direction of the arrowhead on our vectors will indicate the direction of the field at that location. So we're going to have these various points that we kind of choose around the source mass, and we're going to show the magnitude and direction of the field with the length and direction of the vectors that we draw. Again, it's probably going to make more sense when we put a picture up on the screen of what a vector diagram actually looks like. Okay, so we're going to talk specifically today about gravitational vector fields. There will be other types of vector fields that you will learn about if you continue studying in physics. But this is the only vector field that we will look at in this course. We will limit our analysis of vector fields to only objects with spherical symmetry. Okay, I'm not going to ask you to draw a vector field around something that is not spherical. And the field lines that we draw will be radial. Again, that's why we want something spherical and symmetric, because we have these lines and they're all going to be drawn toward that same point or away from that same point, depending on the type of field, but for gravitational, toward it, okay, radially. And so they'll all be like along a line of radius if you were to extend it from the center of that circle. According to the universal law of gravitation, as we move farther away from Earth or any other planetary body, the gravitational field weakens with distance. So how do we diagram that? We just talked about the way that we show strength of the field, and that was with the length of the vectors. And so if it gets weaker as you get farther away, your vectors need to get shorter as you get farther away. This is an example of how you could diagram a vector field around the Earth. Okay, so again, you might want to sketch something like this. You don't have to draw every single one of those arrows or count them or anything like that. Just draw some that are kind of roughly evenly spaced. But you'll notice when you look at this, gravitational fields weaken with increased distance from the source of the field. So here's Earth. Okay, all of these vectors are all pointing toward the center of the Earth, and they're all radial. Okay, so they're all, again, it's all symmetric. And they're longer when you're closer to the Earth, and as you move farther away, they get shorter. The direction of the field is determined by the interaction of objects with the field. You'll notice I have everything pointing toward Earth, and I did that because if you were to place an object in Earth's gravitational field and watch which way it moves, it's going to fall toward the surface. And so everything is going to move toward the Earth's surface when it is being pulled by that gravitational field. So you do need to pay attention to that direction. And again, you can see the magnitudes. It's stronger when you're closer, and it's weaker as you move farther away. And those vectors are therefore shorter. Okay, so how do we find gravitational field strength? I said we're going to talk about that in our notes today. So we have this gravitational vector field. How do we determine the strength of our field? For any object in a field, gravitational field strength can be calculated by Fg equals mg, or if you rearrange that, gravitational field strength little g. By the way, gravitational field strength is little g, different than the capital G, the constant that's in our universal law of gravitation. Please don't mix the two up. Also different than F sub g. That force of gravitational attraction is different as well. So when I say gravitational field strength, I am talking about little g, okay, which on Earth's surface is negative 9.8 meters per second squared. But that is not true if you get farther and farther away. As we just saw, it would get weaker and weaker, okay, as you are farther removed from the surface. Okay, but again, those are the equations that we have already seen in this course, Fg equals m sub g. And again, you can rearrange that to get the other equation that you see there, g equals Fg over m. We also know from yesterday that force of gravity is equal to, so that force of gravitational attraction is equal to our gravitational constant multiplied by the product of our masses divided by the distance between them squared. So, because we have these two equations that both have Fg in them, we can derive another equation that would allow us to solve for gravitational field strength in the event that we don't know Fg and m, okay, or not m, if we don't know Fg. Okay, and so we can substitute in this whole bit right here is equal to Fg. So we can plug it in up here. Again, if gravitational field strength little g equals Fg over mass, here's that Fg over mass. Okay, now how do we know which mass to use? Because there are two. Okay, whenever we're looking at these equations, we're always talking about how that gravitational field is affecting objects that are placed in it. So it's always talking about the object whenever we use one of these equations. Like if you found your weight, it would be your mass times your interaction with Earth's gravitational field, that field strength, okay, which we round to 10. So this mass down here is the source mass, or sorry, not source, the object's mass. I said the wrong one. Okay, so it's m2 down here. So you do need to make sure you understand that if you're trying to derive this equation on your own later on, which you might want to do if you're trying to solve for gravitational field strength and you don't have Fg, then you're going to do this. Okay, now you'll notice when you look at this equation, we can simplify this a little bit because I have m2 down here. I also have m2 up here. It's being divided. I can cancel that out. And when I do that, I end up with a much simpler looking equation. Little g, the gravitational field strength, equals big G, that constant, multiplied by your source mass divided by the distance between the object and that mass squared. That's what the equation ends up being if you derive it. And this, again, shows up in some of that worksheet practice stuff that you were trying to do in my open math the other day. Okay, so how do you find gravitational field strength? Well, if you know these variables, you can use this equation instead. Okay, and of course, big G is a constant. So if you know the mass of that source and you know the distance between the object that you're analyzing in the field and that source, you can plug into this equation. But it's not on your AP Physics 1 formula chart. You have to derive it, just like we did a moment ago. Or you can memorize it. That's fine too. Okay, again, as a reminder, this big G is the constant from yesterday, which is 6.67 times 10 to the negative 11th. The mass that's up here is that source mass, and this R in the denominator is the distance from the source mass. So if you're using that formula, you do need to know what those variables represent. So again, that is an equation you can use for gravitational field strength. All right, so what happens when there are multiple gravitational fields that act at the same location? Okay, you can use vector addition to determine the net gravitational field strength at that location. If you happen to have vectors, then yes, you can add them. And so when you're adding vectors, you'll add them using the tip to tail method. So for example, if I was trying to add these two together, you are going to add them in such a way so that the tip of one arrow lines up with the tail of the next. So for example, like this, I could draw G2 first, and then starting at the tip of this arrow, there's G1. And my net gravitational field strength will be right there, the green one. Okay, the difference of the two because they happen to be in opposite directions. Again, you can see it algebraically right here as well. You don't have to add them in this order. You can add them in any order. I can draw this one first, and then I can draw this one, and I still get the exact same magnitude and direction for that net gravitational field strength. Okay, so again, you can add them with vector addition. Keep in mind, vectors do have direction, so if you're doing it algebraically, you would have to take that into account here. Typically, we'd have to identify our positive direction. One would be positive, one would be negative. So you're truly finding the difference of them in this example. All right, so when we talk about Earth's gravitational field, it is a radial gravitational field, just like in the diagram I showed you. However, everything we've talked about so far, we've been so close to Earth's surface that we have discussed a uniform gravitational field, okay, rather than one that is changing and getting weaker, okay, as you go higher up. And that's because everything thus far has been on the surface. So if you look at it on the scale of where we're at, the gravitational field of Earth does look like this. It doesn't appear radial. It appears to be a uniform field where the field strength is equal at every point. Okay, and again, in order for you to notice those changes in the field, you really do need to be farther removed from the surface where you can have that weaker field strength, or that would be more noticeable. But you would be in space at that point. Okay, so if you're on the surface of the Earth or close to it, then you're going to assume that you have that uniform gravitational field strength, which we have said this whole time is 10 meters per second squared, or 9.8 if you're not rounding it. All right, so let's do an example calculation. This one says, what is the net gravitational field strength on the International Space Station at the position shown? Okay, so you might want to draw the diagram that I have here, because in order for you to solve it, you do need to know the order of these three objects. But I have the Earth, I have the International Space Station, I have the Moon, and I have some distances labeled on my screen. The distance of separation from the Earth to the Moon I have as 3.84 times 10 to the 5th kilometers, and I have the distance of separation between Earth and the International Space Station as 6,963 kilometers, as well as some masses: mass of the Earth, mass of the ISS, mass of the Moon. Okay, so that's what all those abbreviations are referring to. So again, I'm going to use my equation for gravitational field strength that we derived in our notes just a moment ago. The gravitational field strength due to the Earth's mass, we could find this way: the universal gravitational constant multiplied by the mass of the Earth divided by the distance of separation squared. And since we're looking at the effect on the International Space Station, the distance we're going to use is this distance up here, 6,963 kilometers. However, I can't use kilometers, so I did convert it to meters. Okay, again, there are 1,000 meters in a kilometer, so I simply just multiplied by 10 to the third. I know this is not typically the correct notation for scientific notation. You normally want the decimal here, but I just took a shortcut. Okay, so here is my distance of separation. I will be squaring that. Here is the gravitational constant. Here is Earth's mass, and this should give me the gravitational field strength that would be experienced by the International Space Station. Okay, at that distance. If you multiply those values, 6.67 times 10 to the negative 11th, and the mass, 5.98 times 10 to the 24th, and divide by that distance squared, you're going to get this value. The gravitational field strength due to the Earth acting on that International Space Station, that field strength is 8.23 newtons per kilogram. You'll notice that's a little bit less than it would be on the surface, okay? Because on the surface we're at 9.8. Now we're at 8.23. All right, let's go ahead and do the same calculation because we want the net gravitational field strength. The ISS is being affected by both the gravitational field of the Earth and the gravitational field of the Moon, so we need to do the same calculation, but for the Moon. Okay, and so we have now the gravitational field strength of the Moon equals my universal gravitational constant divided by the Moon's, times the Moon's mass, divided by the distance of separation squared. However, the distance of separation is not labeled for this. But I can find it because I know how far the Earth is from the moon and I know how far the Earth is from the ISS, and so obviously I'm looking for that piece right there, which would be the difference of the two with the way that they are drawn. Okay, it's going to be based on the way they're organized in the diagram. So by subtraction, I can find that distance of separation. So I have 3.84 times 10 to the 8th minus this other distance. So I have it subtracted down here. If you want to subtract it first, you can. Okay, but you're going to be squaring the difference eventually. Okay, so again, whenever you plug these numbers into your calculator, 6.67 times 10 to the 11th times 7.35 times 10 to the 22nd divided by that distance of separation squared, you should get 3.45 times 10 to the negative 5th newtons per kilogram. Pretty small number. Okay. By the way, a newton is a kilogram meter per second squared. So a newton per kilogram would be, canceling the kilograms, it's just a meter per second squared. It's the same unit, okay, that we've used the whole time. It's just written differently due to the way the equation is here. All right. So we're not done yet because we have to actually use these values to find net gravitational field strength. But in order for me to do that, I first need to identify a positive direction, because these are directional. Gravitational field strength has a direction. So I'm going to say anything toward the Earth is positive, and thus anything toward the moon will be negative. So when I go to find my net gravitational field strength, and that's going to be the gravitational field strength of the Earth plus the negative gravitational field strength of the moon, because that one's in the negative direction, and you get this 8.23 plus negative or minus 3.45 times 10 to the negative 5th, and guess what? That number is so small that you don't even notice it. It's part of my rounding error, if you will. It's not really error, but you don't see it in the answer unless you report more decimal places than this. Okay, and that's because the gravitational field of the Earth is that much stronger than the moon's, at least with the distances and numbers that I have up here. All right, questions about that calculation? Okay. All right, guys, then for the rest of the class period, you can work on playlist 1. Perhaps you got stuck on some questions about gravitational field strength in your worksheet practice. You can now return to those and hopefully answer them, or take a look at that checkpoint. Playlist 1 is not due until Monday. You could also alternatively use the remainder of the class period to work on your lab, which is due next Tuesday, but you can turn it in tomorrow for feedback. And your bump assignment, probably the most pressing of all if you're planning to do it, is due tomorrow. That's your earliest due date. As a reminder, tomorrow will be a work day in class, so you will also have time in class to work on any or all of these things. I'm going to let you guys get to it. If you have questions as you're working, please let me know.